Hello, my name is Julia Hubble.
My name is Allison Jacobs.
My name is Caitlin Grieve.
And I'm Colleen Lim. So we chose our physics project because we were discussing momentum and Newton's cradle was brought up. And so we wondered if we could make make Newton's cradle on a larger scale using bowling balls, which we did.
So in order to design it, we looked at this smaller model here, and we figured it wouldn't be really reasonable to make on sort of a life-size scale. So what we did instead was we decided to build a bottom frame and then a full top frame, as opposed to these two rectangular standalone pieces here. And then we used the same basic idea for these, which is to take two cables and then have the weight at the end.
So we were lucky enough to get 5 16-pound bowling balls donated from Woodlake Bowling Alley. And Home Depot and Franklin Hardware also donated a lot of materials to help us build the frames and the tools we needed to build it.
In order to construct it, we had us three girls, Caitlin and Allison and myself, Caitlin's father, who we were grateful for his help, Caitlin's little brother as well, who was extremely helpful. I think he made a race car track in here while we were building it. And we also, of course, there was Mr. Centurino, our teacher, and his son. So we all came here on a Saturday at 9 a.m. We stayed until 5 p.m. constructing it. And it just took a lot of drilling and screwing and working with the wood and lifting, but it was fun.
One of the problems we faced was after we had built the two frames, we realized that they were different sizes, and in order for it to work properly, they had to be the same size and line up properly. So we had to undo one of the frames, cut it to be the proper size, and then put it back together. So, but that worked out fine. And then later, when we assembled the entire thing, we realized that one of the bowling balls was not lined up properly with the other bowling balls. So we had to tighten one of the wires to make that right.
So we decided to display the big Newton's cradle outside of our library because we thought that's where the most people would be able to see it. And so when we put it out there, it was right before homeroom, and people from homeroom came out and they were just like, whoa, what is this? And so we put a sign on there saying that it showed conservation of momentum, and they were able to test it out and swing the balls, and that was cool.
And like Caitlin said, when people first saw Newton's cradle on a larger scale, they were really surprised, but they were pretty interested in it. And a lot of the students would walk past it, not sure if they can touch it or not. But they were excited to see it when we actually demonstrated it.
And not only the students enjoyed it, but the faculty did as well. They liked playing with it, and so did the parents who came to the art show. They saw it and had fun with it. So,
Can I tell a funny story? Okay, so when we were building it, we have a top frame and we have a bottom frame, and then we have these steel poles that go around it and make it look kind of like a jail cell. You'll see. And when we put the top frame on, it didn't really fit, and so we needed more weight in order for it to be pushed down onto the steel poles and to have it fit. So at one point, we were all hanging on it. Like, our feet were off the ground and we were all hanging on it, kind of like it was monkey bars. I thought that was really funny.
Okay, and so now we're going to show you how it works.
Momentum is mass times velocity. The momentum of a swinging ball is transferred through the others to the one on the end.
The momentum of two swinging balls is then transferred to the two on the end, the same for 3 or 4.
Also, the number of balls swung at one end will equal the number of balls pushed off the other end.
How fast the ball travels is determined by the height they are released from, as their potential energy is transferred to kinetic energy that the ball possesses upon striking the others.
The balls are each 16 pounds in weight, a little more than the weight of 3 5-pound bags of flour. at 2.2 pounds per kilogram. They are each approximately 7.3 kilograms in mass.
Energy is lost each time they collide, as there is energy lost to sound and heat, thereby eventually stopping the motion. So it's not really a perpetual motion machine, but it's intriguing to watch in action, and it was an engineering challenge to build.
She blinded me with science.
They're hoping to start a craze.
Guys,
Every day.
we should play this on the
A different
lawn.
experience.